Hi all, today we discuss module 2 that contains the chapter 14, the partial derivatives. We start with section 14.3. To define partial derivative, we need to consider a function. So consider a function z equal to f of xy. So the domain of this function is this f is a subset of R cross R, and this is a real valued function. So the image of this function, image set of this function is always a subset of real numbers. So once you consider this function, the meaning of this function is when you consider the graph of this function, you can get if this is our xy plane, this function assigns each point of once you consider this is our function, the graph of the function. That means when you consider each point of this subset of R2, so consider this subset of R2. This is our subset of R2. I consider this is x-axis and this is y-axis. Here we have y prime and here we have x prime. These are x-axis and y-axis. When you consider a subset of xy plane here, I have shaded this region of the xy plane. Corresponding to each point in this plane, we will assign a real number here. So in order to get the images of this function, we consider each point of this subset and the corresponding points in real axis. So once you consider a real axis here, I'll consider a real axis here. So I'll call this real axis as z-axis, and I write it as z-axis. Okay, and this is our z prime. Then you can consider each corresponding to each point here. You consider a real number here and mark it over here. Then you will get this type of instead of a curve, we will get this as a surface. So this is the surface of this function. Okay, this is the idea of a function in R2, okay, or a subset of R2. Now, when you consider this function and fix a point x naught y naught here, say this is our x naught y naught. So once we are going to define the derivative of this function y z equal to f of x y at x naught y naught, we need to consider some limit. Okay. So what is the difference between the limit in real real line and limit in xy plane? When you consider a real line here and fix a point x naught here, then you can consider the limit x tends to x naught in two ways. So this limit can be considered as limit x tends to x naught plus and limit x tends to x naught minus. That means you can approach x naught from the left hand side of this x naught and from right hand side of x naught. Yeah, so this is the only two possibilities in real axis. But when you consider a function whose domain is a subset of R2, R plus R, if you fix a point x naught, y naught in this plane, say this is x naught, y naught, then we consider limit x y tends to x naught, y naught, you need to consider an infinitely many possibilities rather than two possibilities. So here you can approach this point through this way or through this way or through this way. You need not consider only two of these options. From left and right, you can approach from here and here, And there are so many ways, there are infinitely many ways to approach to this x naught y naught. So this is the main difference between the limit in R and limit in R2, R cross R. So this is the concept we are going to discuss here. So in order to approach this x naught y naught, you need to consider so many paths to reach this x naught y naught. Okay, so once you consider a path which is parallel to this y axis and parallel to x axis are very important. Okay, so those will give the concept of partial derivative here. Okay, so once you consider this graph of this function or surface of this function, instead of graph we have here we have, this is the surface of the function. Okay, surface of z equal to f of xy. Okay, now we will define. So in order to consider a limit derivative of a function y equal to f of x in real, so we write dy by dx as a limit. Limit x tends to x naught. Here we have f of x plus or f of x minus f of y or f of x naught divided by x minus x naught. So this is the derivative of a function y equal to f of x in R. But in case of R2, we need to consider df by d at some variable. I'll write it as x. Then we need to write limit x tends to rather than this, instead of this x tends to x naught, we need to consider xy tends to x naught y naught. Okay, so this limit are entirely different from this. So how you define the derivative of a function in R2? That is the that gives the concept of partial derivatives. Once you consider this this graph or this surface, I call this as a surface of f z equal to f of xy, and you fix a point in the domain of this. I'll write it as a domain of this this function as this one. We can consider this is the domain, and then consider x naught y naught in the domain of the function z equal to f of xy. So when you fix this x naught y naught, you can approach this x naught y naught in several manner. You can approach from this side or this way or this way or this way. So there are so many ways. But once you fix a path, okay, which is parallel to x axis, okay, this path is parallel to x axis, and this path passing through this x naught y naught. So consider a line parallel to x axis and which passes through x naught y naught. Okay. Now you consider the rate of change of this f along this way. Okay. So once you consider this way, the equation of this line gives y equal to y naught. Clear? That is set of all xy such that y is equal to y naught gives the set of all points on this line passes through x naught y naught and parallel to x axis. Okay, now consider by fixing this straight line passing through x naught y naught, which is parallel to x axis, you consider the rate of change of this function f at the point x naught y naught. Okay, to consider this, we need to consider the rate of change of f. When you consider this line, along this line we have y is equal to y naught. So every point on this line can be considered as set of all x comma y naught, such that x belongs to R. This is the equation of the straight line passes through this point and parallel to x axis. So when you consider the function and the images of function, images of the points on this line under this function as x, y naught and f of x naught y naught. So this will give the image of f at the point x naught y naught, and this will give the images of points on this straight line. Okay, as x varies. When x varies, you can get all the points on the straight line. When you consider this difference, okay, this is change in the images of f at the point x0, y0 and the points on the straight line. Once you consider this difference and you consider the denominator as x minus x0. So once you consider x here, this point is x comma y naught, and evaluate the images of these 2 points x naught y naught and x y naught, and take the difference between these two. Okay, and consider this quotient. Then evaluate the limit as x tends to x naught. Okay, when consider this limit, you can say that this x y naught tends to x naught y naught as this x limit x tends to x naught. Okay, this is the rate of change of the function f, which is parallel to otherwise along the along the straight line parallel to x-axis and passing through x naught y naught. Okay, so this rate of change, this is the rate of change of f by fixing a particular path or particular direction. Okay, and this is what we call the partial derivative of f with respect to x. This is with respect to x because of we considering this straight line which is parallel to x-axis. So rate of change of f along this line which is parallel to x-axis. Okay, so this is what we call this is actually rate of change. Instead of d by df by dx, we write dou f by dou x. This is partial derivative of f with respect to x. Okay, this is actually to distinguish the total derivative of or this will give the rate of change of f along a direction. Okay, that is in the direction of x. Once you fix a line parallel to y-axis, then which passes through this x0 y0, and consider all this, in that case we can say that dou f by dou y, that can be defined as limit y tends to y0 f of x0 y. This will give the image of points of all the points in this straight line which is parallel to y-axis minus f of x0 y0. So this is the image of image of the point x0 y0 whole divided by y minus y0. Okay, this will give the rate of change of f along the straight line passes through x0 y0 and parallel to y-axis. So this is what we call the rate of change, partial rate of change of f along y-axis. That means partial derivative of y with partial derivative of f with respect to y, and this is what we call partial derivative of f with respect to x. Okay, this is what we are going to discuss in this section, partial derivatives. So next we can define the formal definition of these two. This is the formal definitions of partial derivative with respect to x and partial derivative with respect to y. So this is the definition. Partial derivative, this is partial derivative dou f by dou x at the point x0 y0, that is limit h tends to x0. This is analogous to the case when you consider partial dou f by partial rate of change of this with respect to x. We can consider the same as limit x0, this x tends to x0, f of this is x comma y0 minus f of x x0 y0 divided by x minus x0. By putting this x minus x0 as h, we can get this formula. So this is limit x tends to x0, and we'll put here x minus x0 is equal to h. Then this will be this x can be written as f of x0 plus h comma y0 minus f of x0 y0 divided by h. When this x tends to x0, you can say that this h tends to 0. So this changes to h tends to 0. Now you'll get this one. So these two, we can say that these two statements are same. So derivative of partial derivative of f with respect to x at the point x0 y0 can be written as f of x0 plus h comma y0 minus f of x0 y0 whole divided by this h. Okay, that is same as this one. Similarly, you can define the partial derivative of f with respect to y, that is dou f by dou y at x naught y naught, that is the derivative of the function, the total derivative of the function f of x naught y. So here we fix x naught rather than y, and we consider the rate of change of this function with respect to y. So that will give, this is y equal to y naught, limit x tends to 0 x naught comma, here we have y naught plus h, this is minus f of x naught y naught divided by h. Okay, so this is same as, you can consider the other formula, the partial derivative of f with respect to y is equal to limit y tends to y naught f of this x naught is fixed here, and y, instead of y naught we write y here, and here we have x naught y naught. So this is the difference of f along the value of f along a straight line which is parallel to this y-axis. When you consider the straight line parallel to y-axis, then you can write it its equation as x equal to x naught. Then this x can be replaced by x naught, here also x naught, whole divided by the difference between y coordinate, y minus y naught. Similarly, you put y minus y naught is equal to h, you can get this formula. Okay, so this is the definition of partial derivative of f. The next class we will discuss how to find partial derivative of function, and we will consider a couple of examples for that.